Hello everyone, it's 1 p.m. Eastern and that means it's time to begin another of our monthly CoCoRaHS Weather Talk webinars. Thank you for joining us today. I'm your host Henry Regis, and joining me in the studio is CoCoRaHS founder Nolan Duskin. Running the technical side of our program is our very own Noah Newman. We're coming to you live from the Colorado Climate Center here at Colorado State University in sunny Fort Collins, Colorado. For those of you who are unable to join us for our live broadcast, we'll be recording it for future viewings on our website. All of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, during today's webinar, we're going to talk about the North American monsoon. And how many of you out here are familiar with the North American monsoon? We're excited to have with us today Christopher Castro. And Chris is a faculty member in the Department of Atmospheric Sciences at the University of Arizona in Tucson. His group's current research focused principally on physical understanding and prediction of climate in North America through regional atmospheric modeling and analysis of observations. In addition to his research in Arizona, he is also working to develop improved capacity for weather climate research in other parts of the world, especially Latin America. And Chris tells me that he just finished up recently his sabbatical as a Fulbright scholar at the National Autonomous University of Mexico in Mexico City, where he is working on the monsoon there in Mexico. Well, welcome, Christopher. Thank you for taking the time to be with us today. We're really glad to have you. Christopher, are you there?
I believe Chris is still muted here. Let's see if we can...
Okay.
There we go.
Okay, can you hear me?
We got you. Very good.
Okay, great.
Hey, Chris, I've got to ask you a quick question. How did you become interested in the Southwest monsoon? What got you interested in this subject?
It's a funny story. Is when I was about 15 years old, it was my first time traveling to southern Arizona, and I was traveling with my godparents in Ajo, Arizona, and what I remembered was the people were great in southern Arizona, but the weather was great too. And so I remember sitting and we were having a carne asada, and I saw in the distance these big monsoon thunderstorms forming right at sunset, and so you could see the glint of the sun right off the clouds, and I thought that was one of the most prettiest things I'd ever seen. And then a little bit later that same evening, it was the heaviest rainfall I'd probably ever seen, and it was just amazing to me we could get these really severe flash flood type thunderstorms in the middle of the desert. And I was fascinated ever since. And it just, ironically, I became interested in meteorology, and that became the subject of my research for the past 15 years.
Wow, that's a great story. Well, we're glad you became interested, and we're looking forward to what you have to say today. So go ahead and take it away.
Can you see my screen?
We can, and if you'll just go to the slideshow there, I think we're ready to roll.
Okay, well, thank you very much for inviting me to give one of the webinar series. And I hope you find this interesting. And what I would like to talk about today is first, what's a monsoon and why is there one in the Southwest? And then talk a little bit about how our monsoon storms form, especially with the focus here in Arizona, some monsoon severe weather hazards, and then this question, is it predictable from a seasonal forecast standpoint? And then the big elephant in the room is, what about climate change? And there is some new emerging research about climate change that our group has done and others have done, and I will save that to the end. And then I'll mention a few of our ongoing research topics at the Department of Atmospheric Sciences here at U of A. So first is, what is a monsoon? And you might find various definitions in the literature, but the way I view it is it's a regularly occurring seasonal shift in the winds typically accompanied by large changes in temperature, humidity, and rainfall. And it's derived from actually the Arabic word mausim, which means season. So when you're saying monsoon season, it's actually redundant from the standpoint of what the word monsoon actually means. So to understand what causes the monsoon, we first have to understand the concept of a thermally direct circulation. So this concept is key to understanding how the large-scale circulation changes on a continental scale, and then also how individual monsoon storms form. So here's the concept, and it's basically a convective cell. So there's a difference in the rate that land heats faster than water because of its lower specific heat capacity. So you have hot air that tends to form over the land during the heating of the day, cold air during the water over the water where the air tends to be more dense. This difference in density, the difference in temperatures, causes rising air to form over the land and air to sink over the water. As air rises over the land, it rises and cools to form clouds as the water condenses. So on a daily scale, we observe this in terms of the sea breeze circulation. So the air heats faster than the surrounding water. Air rises over the land, forms clouds, and you typically get sea breeze thunderstorms that occur in the mid-afternoon if you're in a location like Florida, for example. And this circulation would reverse at night as the land cools faster than the surrounding water. So if we're talking about an area with complex terrain, we have a similar concept in the mountain valley circulation. And in this case, the mountains are, you can view them as kind of like heaters in the atmosphere. They're heating faster relative to the surrounding atmosphere. So this causes warm air to be drawn up the slopes, and clouds form right over the peaks of the mountaintops during the heating of the day. So you can view a monsoon as like a combination of a sea breeze and a mountain valley circulation, except we're dealing on a continental scale. So the strongest monsoon, as I'm sure all of you are aware, is in India. And why is that? Is in the north of India, we have, to the north of India, we have the Himalayan mountains and this big giant land mass called the Plateau of Tibet. That Plateau of Tibet has an average elevation of over 15,000 feet and a horizontal extent of more than 1,000 miles. So the contrast between the elevated plateau and the surrounding bodies of water south of India sets up a big giant thermally direct circulation. So the Tibetan plateau is relatively warmer than the surrounding ocean off of Asia. The warm air over the plateau is relatively less dense, so the wind flows from the ocean towards the Tibetan plateau. And this onshore flow transports moisture deep into the interior of Asia. So here's an image of the Indian monsoon just from an infrared satellite image back in 2009. And what you notice is, yes, there's clouds that cover the Indian subcontinent, but there's very high spatial structure in these clouds. So what is actually causing the rainfall are thunderstorms at what we call the mesoscale. So scales of like 1 to 100 kilometers. So the monsoon in India is really wet. So if we look at one of the wettest places on Earth in Cherrapunji in India, this is right near the base of the Himalayas, we can see that we get up to more than 120 inches of rainfall during the peak of the monsoon in July in India. And notice in the dry months of January and December, hardly any rainfall at all. This is just remarkable. And so when the monsoon is really wet in India, this is can be a cause of very severe flooding, and we actually see the same kind of thing in the Southwest. So now shifting to our part of the world, why do we have a North American monsoon? Well, similar to Asia, we do have a giant elevated plateau in the western U.S. and Mexico, but in our case, it's about maybe half as high, about 4,000 to 7,000 feet in elevation, but it really depends on where you are. But it is high enough that we can have this regular seasonal reversal of the circulation. So here's the average flow near airflow near the surface, and what you see is we have low-level moisture transport from both the eastern Pacific and the Gulf of California into the low desert regions of Arizona, and that's mainly to the west of the Continental Divide. And east of the Continental Divide, we have low-level flow from the Gulf of Mexico that penetrates into West Texas, into New Mexico. So also we have to consider the changes in upper air circulation. So as the monsoon develops, there's an upper level subtropical ridge of high pressure that forms over western North America. So before the monsoon, when this ridge is suppressed in central Mexico, the region here in the southwest experiences westerlies aloft, and these westerlies aloft are transporting relatively dry and stable air from the eastern tropical Pacific into the southwest. This has little moisture and is not conducive for precipitation. However, when the monsoon ridge shifts a little bit further to the north, such that we get easterlies aloft over the southwest, that transports upper level moisture from the Gulf of Mexico. And as soon as this ridge gets in the correct position, this is typically the start of the monsoon, which can occur anywhere from late June to early July. So when very similar to India, when we look at the enhanced infrared satellite image sample of a monsoon thunderstorm day over the southwest, we see that, yes, there's clouds over Mexico and western Mexico in the southwest, but what actually causes the rainfall are these smaller scale storms that are occurring at what we call the mesoscale, which is about 1 to 50 to 100 kilometers. So as the monsoon gets going here in the southwest in late summer, the rainfall correspondingly decreases in the central U.S. with the evolution of that upper level ridge of high pressure. So here you see the summer, on the left, you see the summer average rainfall over the contiguous U.S., and you see the signal of the North American monsoon that's more in Mexico, but it extends into the southwest United States. And then with rainfall amounts in central Mexico on the order of 100 to 200 millimeters, and especially in the mountains. And then as the monsoon gets going, what you see on the right is the difference in precipitation during the monsoon in late summer versus before the monsoon in early summer. And you see that precipitation increases in the southwest and in northwest Mexico during the late summer, and decreases correspondingly in the central U.S., particularly in central Texas and Oklahoma. So it's important to recognize we are talking about the southwest in this presentation, but the core of the monsoon is really in northwest Mexico, not the southwest U.S. So if we're talking about northwest Mexico, the monsoon is accounting for about 60 to 70% of the rainfall there. So what you see here are plots of the monthly mean rainfall at several different locations within Mexico. So I've indicated some specific geographical reference points. One over the Mexican Plateau, one over the Sierra Madre Occidental, and then one over Baja California. And what you can notice is there's a great geographic variation in the amount of monsoon rainfall across Mexico, where the majority of precipitation is centered right in the mountains. So if you look at the location in the Sierra Madre Occidental, we're experiencing upwards of 250 millimeters of rainfall in a month during July and August. If we go more away from the mountains, precipitation follows the same seasonal cycle with this rapid jump in June and July, but the precipitation amounts are much less. So this is well illustrated. So this is when I was actually during the North American monsoon experiment in 2004. I was launching weather balloons in Los Mochis, Mexico, and I took a drive up to Choy, which is located in the Sierra Madres. And what you can see is I've shown snapshots of the landscape going from the coast along the Gulf of California up into the mountains. And you go from this very dry desert scrubland type environment to the time you get up into the Sierra Madres is very green and lush vegetation once the monsoon gets going. And this is a stark contrast, and you're talking on the order of less than 100 miles. Now, if we're talking about Tucson, the monsoon in Tucson is now officially defined as a period that starts from June 15th through about the 15th of September. So, but most weather forecasters still go by what the old definition of monsoon onset is. And that was when the dew point exceeds 54 degrees Fahrenheit for 3 consecutive days. And so this is an example of the daily average dew point tracker for the 2006 monsoon. And you see the green line, the solid horizontal green line indicates the 54-degree dew point threshold, which in this case was indicated an early start to the monsoon on June 28. But you can see here that going by the average red line, the monsoon here in Tucson typically, by the dew point definition, starts around July 4th and then ends around the middle of September.
Chris, quick question on that 54 degrees. Will that vary in other states in the Southwest? So say Colorado, would it be 54 as well, or just for the Tucson?
No, correct. These dew point thresholds vary depending on where you are. So in Phoenix, it's slightly more. In other locations, it might be slightly less. You have to adjust for the local climatology when you're doing this.
Thanks.
Okay, so returning to this concept of mountain valley circulations that trigger monsoon storms, recall that what I said earlier is the mountains act like heaters, so they're heating and cooling faster relative to the surrounding air. So when they heat during the day, they draw the warm air up their slopes, and this rising motion forms clouds that occur right over the peaks of the terrain. So if we're talking about Tucson, for those of you that are unfamiliar, we're surrounded by mountains on 3 sides. So these mountain valley circulations play a very big role in our weather, especially during the monsoon. So I've indicated here on our satellite image of the Tucson, Arizona area, we're actually located in a bowl where I've indicated where the University of Arizona is. We're sort of in what they call the Midtown area of Tucson. But on the northwest side of Tucson, we have the Catalina Mountains, which are about 7,000 feet, the Rincon Mountains directly to the east, which are a little less high, and then to our south, not indicated on the map, are the Santa Rita Mountains, and then to the west are the much smaller in elevation Tucson Mountains. So these Catalina Mountains, Rincon Mountains, and Santa Ritas are typical initiation points for convection during the day. So let's just review kind of some cartoons of how monsoon thunderstorms form, and then we'll look at some animations. So first, right before the monsoon, this is when we experience our hottest and driest time in Arizona, where the air is warm and dry and sinking aloft. And we still have air rising along up the mountains, but we typically get very flat type cumulus clouds that don't develop into precipitating thunderstorms. However, once the monsoon gets going, we have colder and moister air aloft that causes, with the diurnal cycle of convection, warm and moist air to rise along the mountains. Storms start to form over the peaks of the mountains in the early afternoon. Now, on a really good monsoon day, the storms will roll off the mountains and into the Tucson Basin by early evening. For this to happen, you need strong winds, relatively strong winds aloft that will help push the storms and propagate them off the mountains and into the urban areas and the low deserts. On a really good monsoon day, when we have very strong thunderstorms and organized convection, the outflows from these storms may trigger new storms even further west, away from the mountains. So these moist outflows will be sources of lift to trigger additional lines of thunderstorms at places relatively far away from the terrain. So for example, in Casa Grande, which is located about 60 to 70 miles away from Tucson. So here is a radar reflectivity image from a sample monsoon thunderstorm day in July of 2009 in the late afternoon, about when the convection starts to peak along the terrain. What you see is the K Tucson is in the center, and very much as I said before, you can see to the north and west and then to the east along those initiation points of convection, and the Catalinas and the Rincons, that's where the monsoon thunderstorms are developing. And notice the very small scale nature of these storms. So you typically will hear the phrase, it rained at my house but it didn't at your house. So that can happen quite a bit. Monsoon storms are very localized here in Arizona, and as I will say a little bit later, it makes them incredibly difficult to precisely predict where the maximum and rainfall will occur. So I'll play a cloud movie, and these are animations that are filmed from the top of the Gould-Simpson building at the University of Arizona, looking northeast towards the Catalina Mountains. So as you recall, this is the point of convective initiation. So we'll play one animation of July 7th, 2009, and I'll give some running commentary as the animation goes on. You just bear with me. Can we see the animation, Henry?
Yeah, it looks good.
Okay. So I'll blow this up. So these start in the beginning of the morning. So you see the timestamp on the lower right-hand side. So right now we're about 7:30.
We're looking north, is that correct?
North and east.
Northeast, okay.
Yeah, from the University of Arizona. So right as the time we get towards 8 o'clock, and if we have clear skies in the morning, you see immediately, and during the heating of the day, you see these convective clouds that start to form over the peaks of the terrain, as I said before. And the nature of it is, when you look at it this way, you can really see it's bubbling convection. And it goes up and down and up and down. And when it goes up and down, it's continually moistening the atmosphere, priming it to get the clouds a little bit deeper as the day goes on. So by the time now we're at near noon, and eventually we'll get to a point where the clouds will reach their level of free convection, and then you'll see thunderstorms start to rapidly develop as the updrafts start to shoot up towards the top of the troposphere. Maybe we need a little longer for that to happen. There it starts to go. And you see as that happens, you start to see these flattening anvils to the storms as they start to hit the top of the troposphere. And the direction of where those anvils go is an indication of the upper level winds that are pushing the storms.
So, Chris, you would need an easterly wind to bring them into the Tucson area, or a northeast wind?
Typically, but this animation is a little unique in that this was a day where we had westerly winds, but it was actually a good monsoon day. So this is actually, it's a nice animation in terms of the clouds, but the direction of the shear of the winds, upper level winds on this day was actually a bit unusual. But there you go. You see the storms developing and the anvils forming.
How far into the night do these go? Do they after dark kind of peter out, or?
It depends on what kind of day you have, but typically we get our monsoon rain in Tucson, and you can see it right here. It's occurring around late afternoon to early evening, and there's the rain in the northeast side of the city, and then it's gone. Okay. So when we're looking for conditions for really good monsoon storm days, this is a combination of features at the large scale and the mesoscale. So we have first an upper level disturbance that travels along the southern side of the monsoon ridge. So you can see these swirls in the clouds where I've indicated the center of the shortwave disturbance. We call this feature specifically a transient inverted trough. We also typically have low-level moisture that surges up the Gulf of California. So the passage of tropical disturbances near the mouth of the Gulf of California, for example, in this case, you can see there's a tropical cyclone off the coast of Mexico. This increases the difference in pressure from the northern to the southern end of the Gulf and triggers a surge of moisture that pulses up the Gulf over the course of several days. So in this case, when we have an upper level disturbance and this low level moisture surge up the Gulf, we can get thunderstorms that originate on the mountains like the Mogollon Rim, and then they intensify and organize as they move westward towards the low deserts and the Colorado River Valley. So here is an active monsoon day animation. So I'll play this several times. So here you see the upper level disturbance over West Texas, and then you see the blowup of organized convection, mesoscale convective systems here in Sonora and Arizona during this day. I'll play it one more time. So there's the upper level disturbance, and on the west side of this disturbance, you have enhanced upward vertical motion from the disturbance itself, and then you also have favorable wind shear profiles to facilitate organized convection. Okay, now shifting to monsoon severe weather hazards. The first is flash flooding. And this occurs in arroyos, canyons, and dry riverbeds. These are typically dry throughout most of the summer, and then you get a really big monsoon storm, and these dry riverbeds suddenly become raging rivers. So here you see on the lower right-hand side, the Rillito River, I believe that's the Rillito River in Tucson during one of these flooding events. You see that it's gone from a completely dry riverbed to nearly a raging river. And this can happen within less than an hour, so you have to be very careful that you don't get caught in one of these things. In Arizona, we have what's called the stupid motorist law, that if you try to cross areas that are marked off for flash flooding, you will get fined because you're crossing the water at your own risk, and you'll pay for the cost of your rescue. But this tends to happen every year, and here's an example from the Las Vegas flood in July of 1999. Henry, are we still seeing my screen?
We are, yeah.
Okay, okay. So another danger is these debris flows. So monsoon thunderstorms are occurring in mountains that have really steep terrain, and the soil is pretty hard and dry, and so it doesn't hold water very well. So what this happens is the water has to go somewhere, and it causes rapidly moving flows of rock and mud and water. And it's a real problem in very steep canyons. So we have one canyon in Tucson called Sabino Canyon, which is located to the north and east of the city, where we had a really dramatic flood in 2006 with a massive debris flow that that caused severe damage to the road and was actually associated with that flood that you saw in the previous slide. So when you look at the landscape, you can see these little rivulets of where we've had the previous debris flows. So those little brown lines in the mountains. So this is the landscape preserves some knowledge of the monsoon storms and these debris flows. You can actually, when you actually go and see what these brown areas look like on the left side of the map, they're large debris flows, and you can see the size of the boulders relative to a person. Another danger is microbursts. So this is where precipitation in the downdraft part of the thunderstorm evaporates partially or fully before it hits the ground, and then the cool air sinks rapidly towards the surface. So you can have dry or wet microbursts depending on whether you have precipitation or not. On the right-hand side of the slide here, you see an example of a wet microburst occurring near the Tucson Mountains. This is actually near where I live, near Bryan Field. You can see very well-defined downdraft, and then a gust front that defines the head of the microburst here as it hits the ground. One of the major dangers here in Arizona are dust or sandstorms, and they have a specific name which is also derived from Arabic called a haboob. So these are caused by rapid movement of air associated with a dry microburst, and as that air hits the ground and it kicks up a big wall of dust, and this typically happens as the monsoon is getting going late in June or early July, because the soil we're coming out of the hardest and driest time of the year, and the soil is pretty dry, and areas, particularly between Tucson and Phoenix, are degraded agricultural land where the soil can be easily lofted by these outflow boundaries. So this is really an example where human disturbance of the landscape has actually worsened one of these dangers associated with monsoon thunderstorms. Hail is another danger, although not so much as pronounced as with storms in the Midwest or in the East, for example. But it does occur from storms that have the highest cloud tops, and these largest storms have very strong updrafts which allow for extended growth of ice particles. But large hail is pretty rare in Arizona, so we typically have pea size or less. Enough to damage cars in the worst case, for sure. Lightning is a discharge of electricity or spark that usually occurs in thunderstorms, principally over land, because we have ice phase processes in clouds. And only about 20% are cloud to ground, but when these things strike, realize the temperature in the bolt is 5 times hotter than the sun. Now, surprisingly, the two lightning hotspots in the United States during the summer, one is certainly Florida, but the other, surprisingly, is Arizona. And here you see for a number of total lightning strikes in July and August from 1995 to 1999, and what you notice is very similar to the monsoon storms themselves. The maxima in lightning tend to occur near the peaks of the terrain where the storms develop. So what's interesting and what we're currently exploring is whether these lightning strikes can be used as a proxy for rainfall to help improve quantitative precipitation estimation, for example, in areas of complex terrain where we might have radar beam blockage. So why more here? We have the elevation, or why more lightning in Tucson relative to Phoenix, for example? We're at a higher elevation, we're closer to the mountains, and we just have more rainfall. Now, during the initiation phase of the monsoon, lightning can be a particular danger in terms of a trigger for wildfire. So lightning-induced wildfire, most acute right before the monsoon, so that could in the period from mid-June to early July. So the factors here are we have dry thunderstorms that produce lightning and wind, but little to no rainfall, and these are often associated with dry microbursts. And again, they're occurring in late spring to early summer, and that's the hottest and driest part of the year. And here you see an image of the Cave Creek fire that occurred in late June of 2005. One of the most infamous examples of this was the recent fire that killed the firefighters near Payson, Arizona, that was caused by a scenario similar to what I'm describing, monsoon thunderstorms forming over complex terrain in a very dry, relatively dry lower atmosphere, and those poor firefighters were caught in a dry microburst in a very steep canyon, and which forced the fire right down the slope, and they unfortunately were caught and were not able to escape. So is the monsoon predictable? So it depends, and this seems to be always the meteorologist's answer. So first, on the daily time scale, can we forecast monsoon storms perfectly exact every day in terms of their pinpoint location? And the answer is no. And even the most sophisticated, highly resolved atmospheric models can't predict the timing, location, and intensity of storms with absolute certainty. But that being said, we certainly can predict generally whether it's going to be an active or down day in terms of monsoon storms and some general geographic areas where convection is most likely to occur based on where the moisture is in the atmosphere and how well that is represented in high-resolution numerical models. Now, what about on a seasonal time scale? So this is how wet or dry is a total monsoon going to be? And the answer here is maybe. And the reason is that, as you recall, what drives the monsoon at upper levels is the positioning of the North American monsoon ridge. So this controls whether we get upper level moisture that comes into southwest from the Gulf of Mexico. So there's the strength and positioning of the monsoon ridge are related to what we call remote forcing from the Pacific Ocean and perhaps even the Atlantic too. So this causes the monsoon ridge to be strong and occur early, or to be suppressed and delayed. In the El Nino type years, we tend to have a trough over the western United States, an extended wet period in the central United States, and dry and delayed monsoons. And in the La Nina type years, we tend to have wet and early monsoons in Arizona and dry, corresponding dry conditions in the central United States. So what about climate change? So the conclusion of the IPCC, and this is a bit dated slide, but it basically hasn't changed from the latest version, that anthropogenic activities have caused the observed global warming with a fairly high degree of confidence over the past 50 years. So when we look at projected U.S. warming, even in a reduced emission scenario, the western part of the United States is warming the most of anywhere in North America. And this is actually very consistent with currently observed trends over the past 20 years or so. Now, the well-accepted conclusion from these global climate models is that, at least on an annual basis, the Southwest precipitation in the Southwest will decrease, and this is mainly due to changes in the large-scale circulation structure associated with the retreat of the jet stream and less passage of synoptic scale mid-latitude cyclones through the Southwest. So that's actually fairly certain in terms of a projection from these models. But a big caveat is that these global climate models do not represent summer rainfall processes well, and that includes the summer monsoon in Arizona. So our starting point for understanding what these global climate models tell us in terms of changes in monsoon precipitation, this is from the latest round of global climate models used for the 5th IPCC assessment report, or Intergovernmental Panel on Climate Change assessment report. And you see the changes in precipitation from 2080 to 2099 versus 1980 to 1999. And these are average over an ensemble of 20 of these global climate change projection models. And the stipples, the dots, indicate areas where there's broad model agreement about what is going to happen. And so what these models tell us is that there is a greater seasonal contrast in the monsoon with drier conditions right as the monsoon is developing in June and July. Notice really substantial precipitation decreases in July, but then in the later part of the monsoon, as the precipitation gets going, there's increases in monsoon precipitation in September and October. Now these study focus more on the monsoon in Mexico, but you can see from the patterns of the differences that these changes are translating, at least in these model projections, a bit into the Southwest United States as well. But this general idea of that there's a greater contrast between the wet and dry times of the year and greater amplification in the seasonal transitions associated with the monsoon, that's an idea that I think is pretty robust. And another idea is that because a simple fact that the atmosphere is becoming warmer, it has greater water vapor holding capacity, we know that precipitation associated especially with heavy events is increasing, and we know that this is occurring throughout the United States and the world. In our own study, looking at observed changes, and this is not model results, this is actually analysis of gauge-based precipitation data, and if we assume that global climate change is affecting climate over the past, observed climate over the past 20 or 30 years or so, our assertion is that perhaps during the last 20 or 30 years, we're seeing the signal of global climate change and what's happening in our warm season precipitation. So looking at the differences between these present and past periods, you can see that precipitation, the precipitation is tending to increase in areas that are climatologically favored to be wet in accordance with their seasonal evolution of precipitation. So in early summer, that's the wet season in the central United States. Precipitation is increasing in the southern Great Plains, and actually there you can see a little bit of blue area here in southern Arizona. But then as the monsoon gets going in the right in August and September, we see increases in precipitation in areas that are already climatologically favored to have monsoon precipitation. So that's Arizona, New Mexico, Utah, Colorado, and Wyoming. But outside of those areas where monsoon precipitation is not climatologically favored to occur, those areas are getting drier. So we seem to be going toward a world with greater seasonal contrast in rainfall and greater spatial contrast in areas that are tending to be wet versus areas that are tending to be dry. And this idea comports with sort of a general principle of climate change that wet gets wetter, dry gets drier. And we tend to be seeing this in the contiguous United States in the observational record. We also, other research that we've done indicates that monsoon precipitation is what I call becoming more thermodynamically dominated. So there's actually less tendency to have passage of these transient inverted troughs through the Southwest, which would tend to cause convection to organize and propagate. So this is tends to be causing monsoon precipitation to become more phase locked to the terrain. And so you get more precipitation on the mountains, but perhaps in the mean, less precipitation in the lowland regions so west of the mountains. But because we're still dealing with a very warm and humid atmosphere, when monsoon precipitation does occur, it will tend to be probably more intense. So my current monsoon research ongoing at the Department of Atmospheric Sciences includes high-resolution real-time monsoon forecasts. We're also looking at forecast sensitivity to the specification of the observed data, sensitivity of monsoon storms to urbanization, and high-resolution seasonal forecasts and climate change projection, and how this can be used to translate and inform hydrologic forecasts. So with that, I will conclude, and thank you very much for your attention. I've included my email here and also the information for the National Weather Service Tucson Monsoon webpage. Thank you very much.
Thanks, Chris. Great presentation. Really interesting, and I'm sure a lot of us have learned stuff we didn't even know about with these monsoons. Folks, if you want to go ahead and type in your questions, we'll bring those to Chris. I've got a couple for you real quick before we go to those questions. And where else in the world do we see monsoons? So you know, we talk about India, we talk about the Southwest monsoon. Where else are they showing up?
They occur generally anywhere you have this contrast between a warm continent and a large body of water. So certainly India, I mentioned North America, but there's also a monsoon in South America, there's a monsoon in Africa, and there's a monsoon in Australia.
Okay, great. And the ones, you know, we think of India with the monsoon, you'd probably think the whole continent is really getting deluged, but from what it looks like only mountainous regions. Is that correct? I mean, with the coastal area of India as well?
Oh no, in India, certainly the terrain can be a focal point for convective initiation, but if you're talking in India, very similar to the phenomenon of transient inverted troughs in the Southwestern United States, you have weak disturbances in a monsoon trough in India that trigger bouts of organized convection, and that accounts for the majority of monsoon rainfall there.
So in the U.S., in the Southwest, how far north, what other states? So we have Arizona, probably southern Utah, New Mexico. What about California? I know we get a little bit in Colorado. Where else do we see that?
The monsoon can certainly is in the United States is centered in Arizona and New Mexico. And then its fringes extend into southeastern California, southern Nevada, southern Utah, and southern Colorado. And this can be generally defined as the area that is affected by monsoon precipitation in terms of it has a coherent seasonal signal in the increase in rainfall in the late summer.
And Chris, what's the heaviest you've seen personally from the rainfall 24-hour period or for one of these monsoons?
I think the example I cited in my presentation, the Sabino Canyon flood, was upwards of maybe 3 to 5 inches of rain. So in the mountains, it can be pretty heavy, and
you know, folks, the flash flooding part, it can be raining up in the mountains with the monsoon, and then the flash flood could occur miles away in sunny weather, right? I mean, it's not just under the monsoon.
Absolutely. So, and this is something you have to be very careful about, especially if you're driving near areas near mountains where you have monsoon storms going on. Those floods can come right down off of those mountains and in a period of minutes.
Well, we've got some questions coming in. Oh, go ahead, Noah.
Yeah, I'm sorry. While you're organizing the questions, I had one for Chris as well, if I may. Chris, I wondered how much you cooperate or work with counterparts within the Mexican version of the National Weather Service there. Do you have a counterpart that you work with?
We're trying to, actually during my sabbatical, we were trying to develop that relationship. And they have great interest in implementing a lot of the high-resolution modeling capabilities that I alluded to in my presentation for their operational purposes. So that capacity building in Mexico is actually something that is extremely important to me.
Okay, here's a question coming in. Nancy writes and wants to know, in Phoenix, the timing of monsoon storms seems to have shifted from mid-afternoon to evening or even late evening. What could be the cause of this, is her question.
Well, I don't know that I can cite any specific study that's looked at changes in the timing of storms. What I can say is that our research is indicating that we're getting less frequent passages of these transient inverted trough features. So that's causing the storms to tend to become more centered over the mountains. So with the less on average tendency to propagate off of the terrain. But when they do, actually tend to be more intense. But I can't comment on the changes in the timing. But you do have more of these days where our forecasters say, well, the thermodynamic conditions are right. That is, we have enough moisture in the atmosphere that there should have a good storms, but there's no dynamic forcing.
Debbie writes and says, what about the monsoon moisture that goes up the eastern backside of the Sierras? So places like Bishop, Mono, Carson City, Reno, what do we see there?
It depends on the upper level circulation patterns for a given day. But depending on where that monsoon ridge is positioned, you can have days during the monsoon that get the upper level moisture all the way up into places like Eastern California and Nevada. And those can be monsoon thunderstorm type days in those places for sure.
Okay, and here's one from let's see. Michael wants to know how accurate were the CPC moisture predictions this past summer and early fall?
I don't know that I can comment on that very well, if nothing else, because I was on sabbatical and my mind was focused on Mexico. But what I recall is that the CPC forecasts were tending to project seasonally above normal precipitation, but more centered in the mountain areas. And what I think, this is sort of at least my own observation, is the CPC model forecast. So they run global climate models out for the next 3 to 6 months to generate as part of their generating their seasonal forecast. And what I've observed in the last few years is these tend to have forecasts above normal precipitation, but more centered over mountainous areas. And this kind of makes sense because I think these models are picking up on the changes in the long-term climatology that I alluded to in my presentation.
Thanks. Terry writes in from Texas, and Terry wants to know, is South Texas too far away for monsoon activity?
It's not traditionally considered the core area of the monsoon in the United States. So that part of the world actually experiences its maximum and warm season rainfall during right before we get our monsoon. So you guys get your rain more in May and in June, and as our monsoon gets going, you tend to get hot and dry.
Jordan from the Southeast Regional Climate Center in Chapel Hill has a question, and he wants to know, why do monsoon thunderstorms typically not produce tornadoes? Is it primarily due to the lack of directional wind shear in the Southwest?
I think the short answer is yes. But that being said, there are certain instances where you can get sufficient directional wind shear to trigger weak supercell type thunderstorms. And this has actually been a subject that they've investigated up at the Tucson National Weather Service office, specifically research done by Dave Blanchard, where he's looked at these mid-latitude cyclones and fronts that pass through Arizona actually around this time of year, so September and October, and you still can have a sufficiently warm atmosphere, and then you do have enough vertical wind shear that you can trigger weak supercell thunderstorms in Arizona, and they've actually been observed in places like Phoenix.
Thanks. Here's one from Larry, and Larry's in Kansas, and he wonders how many days can one predict the occurrence of a significant monsoon event? So how often can you do that? How accurate is that?
I would say if we're looking at least on timescales less than 48 hours, predicting general areas where precipitation will occur is actually fairly accurate. So, for example, here at the University of Arizona, we produce short-term 48-hour forecasts that are used by various stakeholders within Arizona water and power providers for emergency hazard preparation purposes. But when we start to look at beyond 48 hours, it gets really problematic to make accurate forecasts of monsoon precipitation. If nothing else, because we're dealing with phenomenon on a very fine scale, and there's a to the specification of initial conditions in these models.
Thanks. Joni writes that she lives in New Mexico, and this is very relevant information relative information for her. How she wants to know, people living in other parts of the country, do these monsoons that don't have monsoons, but the monsoons that occur in the Southwest, will they affect climate change in other parts of the country? That's kind of a tricky question.
I think the general answer is that what our research seems to be showing is that the changes in precipitation are seeming to become more amplified within the evolution of the seasons. So here in the Southwest, we have a hot and dry period right before the monsoon gets going, and then we have our wet period once the monsoon comes. And so what our research seems to reveal is that we're having hotter, drier conditions right before the monsoon, and even wetter conditions, especially in the mountains, once the monsoon comes. So I think the big picture message is you get more when you're favored climatologically to be wet, and less when you're climatologically favored to be dry.
Terry writes again from Texas. He had another question. He grew up in West Texas, but he says he doesn't remember the summer rains being called monsoon rain. Do they have different names for the monsoon in different states? I mean, would they be called something different?
Well, West Texas is sort of in, it really doesn't have the classical monsoon signal and precipitation, and its precipitation there can also, as I said, similar to the answer I gave for the person from South Texas, you tend to get your maximum in precipitation there more in the late spring to early summer, right before our monsoon begins. But that being said, when you have your wet season there in West Texas, it can be on certain occasions pretty wet with large areas of organized convection, and a lot more tendency for more supercellular type convection and severe weather in the form of tornadoes, if nothing else because it's flat terrain with a lot greater vertical wind shear in those when you have the good convective days.
Donald writes in, and he wants to know, with these rainstorms, they're so localized there in Arizona, how do you obtain a reasonable average area rainfall? Good question.
Oh boy, I don't know if I have a good answer to that. And this has always been a problem here in Tucson because our official reporting site is the airport, which always, at least from what I observed, tends to be a relatively drier location to other places. That being said, so a lot of the analysis you see that I presented here is based on processed climatological products that are generated, for example, by the Climate Prediction Center or the Earth System Research Laboratory by NOAA. So I would say if you're looking at climate trends, it's better to use some product that is taking account some spatial averaging of gauge data and also definitely accounting for the effects of the terrain.
And we can always use more CoCoRaHS observers in any area to get that density. So
most certainly, and I would definitely emphasize to your audience that because we're talking about highly localized precipitation and complex terrain, having a great density of station data from citizen observers is very important.
Davis in New York writes, Christopher from Davis, New York writes, and he wants to know, is there a greater potential for positive lightning strikes with the monsoonal storms?
That question I don't know exactly the answer to, but if you write me, I can certainly refer you to our local lightning expert that could provide you a more precise answer.
Great, and we'll be able to give you the email address. Or actually, it's right on the screen right now. If you look, there's Chris's thing. And would that be Ron Holly, that you're our lightning expert?
Ron Holly or Ken Cummins.
Yeah, Ron's done a webinar with us in the past. Here we go. Let's see. Let me get a couple. We got a couple more questions coming in here. Dave from Arizona wants to know: can you predict along the Catalinas? I guess that's how it's pronounced. Catalinas, you must have typo there. The southern Oro Valley tends to be a rain cave, is what he's saying here. Only 2 times in 15 over an inch. Is it set up a certain way where places in the Tucson area, some get more, some get less during these?
Certainly during individual weather events, but what we can say on at least climatologically is that there's a strong relationship between where you are in terms of being on the mountains versus the lowlands in terms of rainfall amounts. So the lower you tend to be in valley areas, especially further away from the terrain, the lower climatologically your rainfall amounts tend to be.
Okay, Chris, can you stick around for a couple more minutes? We've got a few more questions coming in.
Sure.
Okay. Tommy wants to know, and he was wondering, was this a large monsoon season for Tucson? Were there any significant big thunderstorm events?
There were, and during most monsoons there typically are. But in terms of, I think, the seasonal average rainfall, this was a pretty average monsoon.
Okay, Lloyd in Palmyra, New York. His question is orographic lift the same as the heating lift you described? And if not, how are the two distinguished?
Yeah, I think of orographic lift more associated with enhancement of winter snowfall. So you have winds that are forced up the side of a mountain from a large-scale weather system, and that forcing of the winds up the mountains causes the air to cool and condense. What I'm talking about here are the diurnal mountain valley force circulations from the local heating and the cooling of the terrain. So it doesn't have anything to do with the passage of these large-scale weather systems that would cause enhanced snowfall, for example, during the winter.
Scott writes, and he grew up in Phoenix. He said when he was growing up there, he was told that if they had a good wet winter on the rim, we would have a good monsoon season. What are your thoughts on that?
Well, the data actually seem to contradict that, at least. This is some of my own research, is that there seems to be a weak opposite relationship between winter precipitation, or cool season precipitation, and warm season precipitation. So that when we tend to get wet winters, at least the statistics tell us they tend to be followed by dry and delayed monsoons. Again, not all the time, but at least that's what the statistics tell us.
And Debbie wants to know the recent tragedies there near Zion National Park. Was monsoon moisture responsible for those thunderstorms?
Yes. And at the same time, when that happened, there were some of the biggest wildfires raging in California just a few hundred miles away. So I think it's very exemplary of this increase in contrast between regions that are wet or dry. And this is kind of, I think, manifesting itself in the types of disasters and increase in hazards that we're seeing.
Okay, Chris from Griffin, New York wants to know, do you find greater success with non-hydrostatic models when forecasting on the mesoscale level?
In a short answer, definitely. I mean, I think I'm of the professional opinion that you must have what we call the convective permitting scale, where we are what we call explicitly resolving convective thunderstorms within a model, and that requires a non-hydrostatic model where convection is not parameterized.
Okay, and here's one here from Travis, and Travis says, does vegetation affect the monsoon? So areas that are barren versus areas with lots of trees.
Oh, that's an excellent question. And it's currently actually an area of very active research in what is the land influence of the land surface on the monsoon. And what we don't know is once monsoon begins and there's rapid green up of the vegetation, this is totally changing the surface energy and moisture budgets. And we don't really know quite yet how that feeds back, especially on at the climate type time scale on seasonal monsoon rainfall. That being said, research principally by my colleague Francina Dominguez has established that the land surface is probably an important source of monsoon moisture, particularly later in the summer as the vegetation greens up.
Well, Chris, we want to thank you for taking time out of your day today. This was a great webinar. We will archive this and have his slides available and also a recording on our CoCoRaHS Weather Talk webpage. Again, we really appreciate you being with us today, and thank you so much.
All right, my pleasure.
Well, folks out there, please mark your calendars and join us on Thursday, November 12th. That's coming up shortly. The Weather Channel's winter weather expert, Tom Niziol, will give a presentation on lake effect snow. Please note that this webinar will take place 2 hours earlier than our usual time. So if you're on the East Coast, that'll be at 11 a.m. Eastern Standard Time. We'll have let you know how to sign up for that coming up here shortly. And finally, when you're signing off today, please take the survey that pops up on your screen. It's very helpful to us. So until next time, this is Henry Regis for the rest of the CoCoRaHS team saying goodbye for now and have a great afternoon.